Before the dinosaurs walked the earth, sharks were already patrolling the ocean. Before the first tree grew or the first insect took flight, before any vertebrate had made the leap from water to land, sharks were there. They are not just old, they are ancient in a way that is genuinely difficult to hold in your mind. The earliest shark-like fish appeared in the fossil record around 450 million years ago, more than twice as long ago as the dinosaurs, and nearly 200 million years before the first marine reptiles we met in the last episode. To put that number in perspective, the dinosaurs ruled the Earth for roughly 165 million years, and we consider that an extraordinary achievement. The mosasaurs and ichthyosaurs dominated the Mesozoic ocean for nearly 200 million years combined, and their story fills an entire episode of this series. Modern humans have existed for about 300,000 years, and in that time, we have reshaped much of the planet beyond recognition. Sharks have been here for 450 million years. They were swimming through the ocean long before the Tethys Sea opened, long before the supercontinent broke apart, long before any of the great events we have covered in this series. They are not a single chapter in the history of the ocean. They are a continuous thread woven through almost all of it. And here is what makes that longevity even more remarkable. The sharks alive today are not dramatically different from the ones swimming in those ancient seas. The essential design, the cartilaginous skeleton, the continuously replaced teeth, the torpedo-shaped body, the extraordinary battery of sensory systems, was worked out hundreds of millions of years ago and has barely needed fundamental revision since. Evolution has refined the shark over time. It has produced over 500 species across a vast range of sizes and ecological roles. But it has not reinvented the core blueprint. When you look at a modern great white shark moving through cold water, you are looking at one of the most durable and effective body plans in the history of animal life. That durability is not a product of simplicity. Sharks are not primitive animals that have survived by being too basic for evolution to work on. They are sophisticated, complex, and continuously adapting. Their survival through 5 mass extinctions, through ice ages and warm periods, through the repeated transformation of ocean ecosystems across hundreds of millions of years, is the result of a biological toolkit so well designed and so flexible that the ocean has consistently rewarded it regardless of conditions. No other large predator in the history of life on Earth comes close to matching that record. What makes their persistence even more thought-provoking is the context in which it occurred. The Paleozoic ocean, where sharks first appeared, bore almost no resemblance to the modern sea. The Mesozoic ocean, where they shared space with enormous marine reptiles, was a warmer and more biologically diverse world than today. The modern ocean, colder and more structured, is the latest in a long series of very different environments that sharks have moved through and adapted to. The thread connecting all of those worlds is the shark itself. This episode traces that arc from its earliest evidence, examining what the first sharks were, how they spread through the Paleozoic ocean, how they diversified after each mass extinction reset the ecological playing field, and how a combination of biology and flexibility produced an animal line so successful that it has outlasted virtually everything else the ocean has ever attempted at a comparable scale. The shark is not the end product of 450 million years of evolution. It is a continuing project, still being refined, still meeting new challenges. Understanding it means understanding the ocean in a way that nothing else quite allows. Before going back to the beginning of shark history, it helps to be clear about what a shark actually is, because the word covers far more territory than most people realize. The image most people carry is of something like a great white or a tiger shark, a large, powerful, open water hunter with rows of serrated teeth and an intimidating reputation built largely by decades of films and media coverage. That picture is accurate as far as it goes, but it accounts for only a small fraction of what the shark group actually contains. There are over 500 known species of sharks alive today. They range from the whale shark, the largest fish on Earth at up to 40 feet long and weighing as much as 20 tons, to the dwarf lantern shark, a deep-sea species small enough to fit comfortably in the palm of a human hand. They live in every ocean on Earth, from shallow tropical reefs to the deepest ocean trenches, from warm equatorial waters to the near-freezing seas around Greenland. Some sharks live in freshwater rivers. Some migrate thousands of miles across open ocean annually. Some spend their entire lives within a small patch of reef. The ecological and physical diversity within this group is extraordinary and rarely acknowledged. The Greenland shark deserves its own moment of attention. It lives in the deep, cold waters of the North Atlantic and Arctic, moves slowly enough that other animals can ride on it without effort, and grows almost imperceptibly slowly over the course of its life. Scientists estimating its age using radiocarbon dating of proteins in its eye lens tissue have concluded that some Greenland sharks alive today may be over 400 years old. The technique relies on a carbon signature deposited in the atmosphere during nuclear weapons testing in the 1950s and 1960s, which acts as a chemical timestamp in the tissues of animals alive at that time. The evidence suggests that the oldest Greenland sharks may have been alive before the United States was founded, before the Industrial Revolution, possibly before the Pilgrims crossed the Atlantic. These are not hypothetical ancient animals. They are swimming in the ocean right now. What defines a shark as distinct from other fish comes down to a set of shared biological features. Sharks are cartilaginous fish, meaning their skeleton is made entirely of cartilage rather than bone. Cartilage is lighter and more flexible than bone, giving advantages in buoyancy and maneuverability. Sharks also have multiple rows of teeth that are continuously replaced throughout their lives. The front row is always in use, and behind it, additional rows wait in sequence, moving forward as each tooth is lost or worn. A shark may produce tens of thousands of individual teeth over its lifetime, and it never has a dull tooth in active use for long. Most active shark species need to keep swimming to push water over their gills. The streamlined body, the rigid pectoral fins that provide lift, the powerful asymmetric tail that drives them forward, all of it flows from the demands of continuous efficient movement through water. Together, these features produce an animal built for one purpose and built for it with the precision that nearly 500 million years of selection pressure tends to produce. There is one more feature worth mentioning before we go further. The group formerly known as Elasmobranchi includes sharks, rays, and skates. Rays are essentially flat sharks, animals that took the cartilaginous fish body plan and flattened it for life on the seafloor. Many of the features we associate with sharks are shared across this broader group. When we talk about what makes a shark special, Much of its toolkit is shared with rays and skates that have been extraordinarily successful in their own right. Understanding that broader family helps put the shark in its full biological context. The first sharks appeared in the fossil record around 450 million years ago during a geological period called the Silurian. The ocean at that time was profoundly different from the one we know. Jawed fish had only recently appeared on the evolutionary scene, and the early sharks were among the first animals to have them. The ocean was dominated by strange armoured fish called placoderms, by soft-bodied invertebrates, and by the descendants of the Cambrian explosion we discussed in episode 1. It was a world without anything we would recognise as a modern marine ecosystem, and the earliest sharks were themselves strange animals by the standards of their modern descendants. The earliest shark-like creatures we have clear fossil evidence for were small, probably no more than a foot or two in length. Their bodies were covered in tiny, tooth-like scales called denticles. These structures are not scales that happen to look like teeth. They are literally built from the same tissues and follow the same developmental pathway as teeth. Shark skin is, in a very real sense, covered in millions of miniature teeth. It is rough enough to have been used historically as sandpaper, and the particular way it channels water flow across the body reduces drag in ways that engineers are still studying for applications in swimsuit design and aerospace technology. Because shark skeletons are made of cartilage rather than bone, they decay rapidly after death and rarely fossilize intact. What we know about early sharks comes primarily from their teeth and denticles, which are mineralized and preserve well. One of the most complete early shark fossils ever found is Cladocelac, from around 375 million years ago, preserved in the Devonian Age shales of Ohio. Cladocelac was roughly 6 feet long with a streamlined body, 5 gill slits, and a deeply forked tail. It looked strikingly modern, far more so than you might expect from an animal that lived nearly 400 million years ago. The Devonian period, sometimes called the Age of Fish, was when sharks first began diversifying in earnest. At the end of the Devonian, around 360 million years ago, a major extinction event struck the ocean. The placoderms, the dominant predatory fish of the era, were effectively wiped out. The ecological space they had occupied was suddenly available, and sharks moved into it rapidly. By the time the Carboniferous period began, sharks were the dominant large predators in the ocean. The Carboniferous is sometimes informally called the Golden Age of sharks by paleontologists because the fossil record from this period shows an extraordinary range of shark forms, many of them unlike anything alive today. The fossil record of early sharks is also a reminder of how much we are still missing. Teeth and denticles tell us a great deal, but they cannot tell us about reproductive behavior, hunting strategies, migration patterns, or social dynamics. What we can say is that by the end of the Devonian, the shark lineage had already proven itself resilient enough to survive a major extinction and diverse enough to take advantage of the opportunities that extinction created. Those qualities would define the group for the next 360 million years. For most of their history, sharks have not been the giants of popular imagination. The early sharks were modest in size by modern standards, and even through much of the Mesozoic era, sharks occupied a secondary role in the ocean. The mosasaurs and plesiosaurs, discussed in episode 4, were the apex predators during that period, and sharks whatever their other qualities, were not the largest or most fearsome animals in the sea during the age of the great marine reptiles. That changed dramatically after the asteroid impact 66 million years ago wiped out the marine reptiles and fundamentally reset the ocean's food web. In the ecological space that opened up in the aftermath of that extinction, over the tens of millions of years that followed, sharks expanded rapidly into niches that had previously been dominated by other groups. Species grew larger. New hunting strategies emerged. The diversity of shark forms increased substantially. And for the first time in hundreds of millions of years, sharks became the undisputed top predators of the open ocean across its full depth range. The most famous product of that expansion is an animal so large and so embedded in popular culture that its name is recognized by people who have never considered sharks seriously: Megalodon. Formerly known as Otodus megalodon, this animal is estimated to have reached lengths of around 50 to 60 feet, roughly the size of a school bus, making it one of the largest predatory fish to have ever existed. Its teeth, found as fossils on beaches on every continent, could exceed 7 inches in length. The largest great white shark tooth on record measures just over 2 inches. Megalodon's jaws, reconstructed from the geometry of its fossilized teeth, were wide enough to engulf a large person in a single bite. It fed primarily on large marine mammals, particularly whales, and the fossil record contains whale bones bearing megalodon bite marks that penetrate several inches into solid bone. Megalodon lived from roughly 23 million years ago to about 3.6 million years ago, when it went extinct. The most widely supported explanations for its disappearance point to a combination of pressures: a gradual cooling of the global climate that reduced the warm, shallow coastal seas it preferred to hunt in, a parallel decline in the populations of large whale species that formed the core of its diet, and the emergence of new competitors, including early ancestors of the orca, which were faster and capable of cooperative hunting strategies that may have outcompeted even Megalodon for the same prey. There are approximately a dozen other shark species from across geological history that have periodically generated scientific interest as large and ecologically significant predators. Cretoxorhina, the Ginsu shark discussed in episode 4, was an impressive Cretaceous predator. Tychodus, a massive shell-crushing shark from the same period, may have reached comparable lengths. Helicoprion, an ancient shark-like fish from the Permian with a distinctive spiral tooth whorl that still puzzles scientists, demonstrates just how varied the cartilaginous fish blueprint has been across geological time. Megalodon may be the most famous of the giants, but the history of large sharks is far richer than a single animal. What makes sharks such consistently effective predators is not primarily their teeth or their speed, formidable as both are. It's their senses. Sharks possess one of the most sophisticated and comprehensive sensory systems of any animal on Earth, a suite of tools for detecting the world around them that operates across multiple independent channels simultaneously. Understanding those senses is central to understanding why the shark design has proven so durable, and how an animal can be so effective across such an enormous range of environments and across such an extraordinary span of time. The most familiar of the shark senses is smell. Sharks have an exceptional ability to detect chemical signals in the water, and the stories about detecting a single drop of blood from great distances, while somewhat simplified, are grounded in genuine biology. Sharks can detect certain compounds at concentrations of just a few parts per billion. Their nostrils are not used for breathing. That function belongs entirely to the gills, but purely for sampling the chemical environment. They draw water through each nostril independently and can detect which side of their head is receiving a stronger signal, allowing them to follow a concentration gradient toward its source with precision that has no equivalent among land-based hunters. Vision becomes the dominant tool at closer range, particularly in clear water. Shark eyes adjust quickly across different light levels and include a reflective layer behind the retina called the tapetum lucidum, the same structure found in cats that dramatically amplifies their ability to see in low light. Running along both sides of a shark's body is a system called the lateral line, a series of fluid-filled canals embedded in the skin that detect pressure changes and vibrations moving through the surrounding water. When any animal moves through water, it creates pressure waves that radiate outward. The lateral line detects those waves and provides information about the direction, approximate size, and movement pattern of whatever is generating them. The sense that most clearly distinguishes sharks from almost every other animal on Earth is their electroreception, a network of jelly-filled pores concentrated around the snout, called the ampullae of Lorenzini, detects the tiny electrical fields that all living organisms generate simply by being alive. The sensitivity of this system is extraordinary. A flatfish buried under several inches of sand, motionless, completely invisible to every other sense, still produces an electrical field through its heartbeat and muscle activity. A shark can detect it and locate it precisely. This also explains why sharks sometimes bite metallic objects in the water. Metal in seawater generates electrical fields that trigger the electroreception system and register as something alive. It is worth noting that the sensory systems of sharks have not stood still across 450 million years. The ampullae of Lorenzini show significant variation across different species, with deep-sea sharks and open-ocean hunters having different configurations and different sensitivity ranges than reef sharks or bottom-dwelling species. The lateral line similarly varies in its distribution and sensitivity. What this suggests is that while the core sensory toolkit has been present since early in shark history, it has been continuously modified and optimized for different environments and hunting strategies. The shark sensory system is not a single fixed design. It is a platform that evolution has adapted in dozens of different directions, each one tuned to a specific set of environmental demands. Sharks have survived 5 mass extinctions. That single fact sets them apart from almost every other group of large animals that has ever lived on this planet. The end Ordovician extinction, around 443 million years ago, the late Devonian extinction, around 375 million years ago, the Permian extinction, around 252 million years ago, which killed up to 96% of all marine species and is the most severe extinction event in the history of life on Earth. The end Triassic extinction, around 201 million years ago. The end Cretaceous extinction, 66 million years ago, that wiped out the dinosaurs and the great marine reptiles. Through all 5 events, the shark lineage endured. Particular lineages disappeared permanently, but the fundamental design survived every time, and after each extinction, the remaining sharks diversified again into whatever ecological space the recovering ocean offered. How they managed this repeatedly while so many other groups were eliminated is one of the more instructive questions in the history of life, and the answer involves several factors working together. The first is metabolic flexibility. Many shark species can slow their metabolism dramatically in cold water or when food becomes scarce, sustaining themselves for extended periods without eating. Some sharks have been documented surviving for months without food under controlled conditions. In the nutrient-poor, disrupted environments that follow a mass extinction, the ability to endure long, lean periods is an enormous advantage. The second factor is reproductive resilience. Most sharks give birth to live young, called pups, that are fully formed and functionally independent from the moment of birth. Shark pups arrive in the world as small but complete predators, capable of hunting immediately without any parental support. Shark reproduction is slow, litters are small, and gestation periods can be long, but the offspring are robust. This means shark reproductive success is less dependent on stable, favorable environmental conditions than species that require extended periods of parental care. The third factor is ecological breadth. As a group spanning more than 500 species, sharks occupy an extraordinary range of sizes, habitats, depths, and feeding strategies. When one type of marine ecosystem collapses in an extinction event, the shark species specialized for that environment may suffer heavily. But sharks, occupying different niches at different depths, in different temperature ranges, hunting different prey, carry the group forward. There is also geographic range. At various points in their history, sharks have been distributed across virtually the entire global ocean. When catastrophe strikes one region, sharks in other regions survive and eventually recolonize the recovering areas. The recovery of shark populations after each mass extinction also tells us something important about the pace of biological recovery in the ocean. Sharks did not bounce back overnight. The fossil record shows that in the aftermath of each major extinction, shark diversity was low for millions of years before beginning to climb again as the ocean rebuilt. Recovery from extinction is measured in geological time, not human time. This is relevant context for understanding the current situation, where shark populations are declining at speeds driven by human activity rather than geological process, and where any meaningful recovery would require timescales extending far beyond a single human lifetime. Humans and sharks have had a complicated relationship for as long as people have been going into the ocean. That relationship involves fear, misunderstanding, exploitation, and in recent decades, a growing but still insufficient recognition of how essential sharks are to the ocean systems we depend on. Looking honestly at that history means confronting how much damage human perception has done, not to us, but to the sharks themselves. Start with the fear and with what it is actually grounded in. Shark interactions with humans do happen, and when they do, they are serious and sometimes fatal. But the numbers are dramatically smaller than popular culture suggests. Globally, there are typically between 70 and 100 unprovoked shark interactions with humans per year, resulting in around 5 to 10 fatalities. More people are killed annually in the United States by vending machines, by cows, and by lightning. The statistical risk that a shark poses to a person in the ocean is genuinely tiny, and the gap between that reality and the cultural terror that sharks inspire is one of the more dramatic mismatches in modern public perception. Much of that mismatch can be traced to a single novel and a single film. Peter Benchley's Jaws, published in 1975, and the Steven Spielberg film that followed created an image of the great white shark as a calculating, relentless predator of human beings. That image bore almost no resemblance to the actual animal. Great white sharks have no particular interest in human beings as food. Most interactions between great whites and humans follow a bite and release pattern that reflects investigatory behavior. The shark encounters an unfamiliar object, investigates it using the only sampling tool available, determines it is not suitable prey, and moves away. Benchley spent the years following Jaws working actively on shark conservation, expressing deep regret about the impact his novel had on public perception and on the hunting of great whites that followed. Not all human cultures have approached sharks through fear. Polynesian cultures revered sharks as powerful spiritual forces and, in some traditions, as ancestors and protectors. Indigenous coastal communities throughout the Pacific and Indian Oceans developed nuanced, respectful relationships with sharks based on generations of careful observation. The idea of the shark as pure threat, existing solely to endanger human beings, is largely a product of modern Western culture and modern media. The commercial shark fishing industry that developed in the 20th century operated with essentially no regulatory framework for most of its history. Sharks were treated as an inexhaustible resource, as dangerous pests to be removed from fishing areas, and as raw material for commercial products. The idea that sharks required conservation attention, that their populations could collapse, that their removal from ecosystems could have consequences, was not seriously entertained in most policy circles until populations had already declined dramatically. By the time the data became undeniable, the damage was extensive. International coordination on shark conservation has improved significantly in recent years. The Convention on International Trade in Endangered Species has listed an increasing number of shark species under its protection frameworks, restricting international trade in those species. The Convention on Migratory Species has facilitated cooperation between countries through whose waters migratory shark species pass. These frameworks are imperfect and enforcement is inconsistent, but they represent a meaningful shift from the complete absence of international coordination that characterized most of the 20th century. The real danger in the relationship between humans and sharks runs entirely in the opposite direction. We are not meaningfully threatened by sharks. Sharks are in genuine and accelerating danger from us, at a scale that dwarfs any threat they have ever posed to human beings in the entire history of our two species sharing the ocean. Scientists estimate that humans kill somewhere between 70 and 100 million sharks every year. Some estimates put the figure considerably higher. Set against the 5 to 10 human deaths caused by sharks annually, the ratio is almost impossible to process. It represents one of the most severe and sustained pressures on any group of large animals in recorded history, and it is taking place against animals that took 450 million years to produce. The primary driver is the global shark fin trade. Shark fin soup is a traditional dish in several Asian cultures, served at weddings and formal banquets as a symbol of wealth and respect. The demand for it has fueled an industry that catches sharks, slices off their fins while the animals are still alive, and discards the finless bodies back into the ocean, where they sink and die. The fins themselves add almost nothing to the flavour of the dish, which comes from the broth, but their status as an expensive ingredient has proven resistant to conservation pressure. Regulatory action and sustained public campaigns have begun to reduce demand in some markets, but the trade remains substantial. Shark finning is the most visible part of a broader problem. Enormous numbers of sharks are also caught as bycatch in nets and on long lines set for other fish, and many die before they can be returned to the water. The combined pressure across finning, bycatch, and direct commercial fishing has caused the collapse of shark populations across most of the world's oceans. The oceanic whitetip shark has declined by an estimated 98% in the open ocean since the mid-20th century. The great hammerhead is critically endangered. The whale shark is classified as endangered. These animals survived 5 mass extinctions, and they are now being pushed toward elimination within the span of a single human lifetime. The economics of shark conservation deserve attention because they often determine what is actually achievable on the ground. In many developing countries, fishing communities depend on sharks for income and food security. Any conservation approach that does not address those economic realities will fail. Successful programs in places like the Bahamas, Palau, and parts of Indonesia have worked by creating economic alternatives, particularly shark diving tourism, that give communities a financial stake in maintaining living shark populations. A single reef shark, living for its full lifespan and attracting diving tourists, is worth dramatically more economically than the same shark killed for its fins. The science of shark population recovery is also still developing. We know that some shark species can recover relatively quickly when pressure is reduced, while others, those with especially slow reproduction and very long time to sexual maturity, may require decades of protection before meaningful population growth occurs. The great white shark reaches sexual maturity at around 15 years of age and has small litters after a gestation period of about 12 months. Recovering a depleted great white population is a generational project. Knowing this matters for setting realistic expectations and for maintaining political will for conservation over the long term. Sharks tell us something about the ocean that almost nothing else can. They are the long memory of the sea, animals whose biology and evolution have been shaped by 450 million years of continuous interaction with it. When shark populations collapse, when species that were once abundant across entire ocean basins begin disappearing from ecosystems they have occupied since before the dinosaurs, the ocean is communicating something important about the scale and speed of the changes being imposed on it. The challenge is being willing to pay attention. One of the most significant things sharks reveal is the true depth of the ocean food web's history. Sharks did not arrive in an ocean that was already structured the way it is today. They helped build that structure over hundreds of millions of years. The schooling behavior of fish, the camouflage patterns of reef species, the migration routes of marine mammals, the vertical distribution of different species through the water column. All of these patterns have been shaped in part by the continuous presence of sharks as predators. Remove the sharks, and you do not simply produce an ocean that lacks sharks. You produce an ocean whose internal relationships begin shifting in ways that are difficult to predict and often impossible to reverse quickly. Sharks also serve as indicators of ocean health in ways that are just beginning to be fully understood. Where sharks are abundant, the ecosystem below them tends to be diverse and in balance. Where they have been removed, the signs of disruption appear quickly and in unexpected ways. Monitoring shark populations is increasingly used by marine scientists as a proxy for the overall health of the ecosystems they occupy. In this sense, sharks are not just animals to be protected for their own sake. They are instruments for reading the condition of the ocean itself. Sharks also complicate the standard picture of how evolution works. The conventional view emphasizes continuous change and adaptation as the keys to long-term survival. Sharks tell a different story. Their core design has remained fundamentally stable for hundreds of millions of years, not because evolution stopped working on them, but because the design was so effective from an early stage that departures from it were consistently outcompeted. The ocean has transformed around the sharks many times. The sharks have adapted at the margins, producing new species and new prey relationships as conditions shifted. But the essential toolkit has held. It is also worth considering what it would mean for ocean science if sharks were to be significantly reduced or eliminated from large parts of the ocean. Sharks have been part of marine ecosystems continuously for 450 million years. Much of what we understand about how ocean food webs function was developed in a world where sharks were present in their baseline abundance. A world with dramatically fewer sharks would be scientifically unprecedented. The changes that would follow would produce an ocean that looks different from any ocean we have reliable knowledge about. Managing and understanding that ocean would require rebuilding much of our scientific framework from the ground up. For 450 million years, the ocean has had sharks in it. Through every transformation the planet has undergone, through every extinction and recovery, through the opening and closing of seas, the rise and fall of continents, the coming and going of every other large predator the ocean has ever produced, the sharks have remained. They were here before us. They shaped the ocean we inherited. Whether they are here after us depends, more than most people realize, on choices being made right now. In the next episode, we step back to explore the world the earliest sharks entered, the strange and spectacular Paleozoic ocean, dominated by creatures so unlike anything alive today that they read almost like science fiction. Until then, thank you for listening.